Hi, everybody. Welcome back. We're going to keep discussing today about conduction in steady state beyond the 1D. We're going to look into thermal resistance and other aspects of heat conduction in steady state in even very complex geometries. So let's take a quick recap of what we saw on Monday. Um, what we saw on Monday is that the concept of thermal resistance could be extended beyond 1D to pretty much any other geometry because there is disproportionality between the rate of heat transfer by conduction and the temperature difference between two points in this 3D system. There is disproportionality, and we can define now a resistance just as we did before. So if we go and use the differential equation of heat conduction in steady state without heat generation and with radial symmetry, we can define a thermal resistance. Let's get the pointer going. A thermal resistance of a cylinder. And much like we did before defining a thermal resistance per unit area, we can define a thermal resistance per unit length, with the caveat that, again, is in reality resistance times length or resistance times area, and that can be confusing. And we immediately recognize this the resistance of the cylinder because it has a log in the expression. This would come from integrating the differential equation that comes from the differential control volumes unit for cylindrical symmetries. And I made the point that something that is so easy to get confused, that we see a cylinder, and that's what our eyes tell us. There is a cylinder. However, for heat transfer, what heat transfer sees is the boundary conditions. So if the boundary condition says that the inner surface of the cylinder and the outer surface of the cylinder are at different temperatures, then we have heat transfer in the radial direction, and these formulas we have seen on Monday apply. If instead, all across all over the cross section, the temperature is uniform, but the gradient is longitudinal, now actually, despite that the cylinder looks exactly the same one as before, because the boundary conditions are different, because the heat is applied in a very different way, now the heat would be longitudinal and the thermal resistance would be pretty much the same one of a plane wall. And if you see in this expression something that has R2 and R1 square, it doesn't look like the plane wall, but it is, because in the plane wall, the resistance involved the cross-sectional area. And this is exactly what the cross-sectional area is. We mentioned that also, if we we use the differential equation that came from the differential control volumes for a spherical symmetry in steady state and with not heat generation for a constant thermal conductivity. From there, we would obtain a value of the thermal resistance for radial heat transfer in a sphere. And we have the expression here. What you're gonna see in this course as we move forward is something interesting, that we went very deep in the fundamentals. It's important that you handle these fundamentals well. And we do a little bit of math. We have solved the differential equation for plane walls, have solved differential equations for lumped capacitance, for the assignment 1, you're solving the differential equation of second order that corresponds to fins, right? And you have in the book how you solve the differential equation for spheres and cylinders. Now, up to that level, I know we can be together, but you're gonna see that the equation, the boundary conditions get more and more complex with different geometries. And it gets to a point in which we're gonna know what the original equation is, the differential equation. We are not going to solve it ourselves, but we're gonna use the solutions that somebody, probably a grad student in some long time ago, suffered a lot to do it. So we know where to start. We're gonna skip the math in many cases and land in the solution that somebody spent a lot of time getting. A little bit of a taste of this is what we're doing here. We know the differential equation for sphericals in spherical coordinates because we did it in the section on differential control volumes, especially when we have spherical symmetry. The solution of that equation that we know how to write because we did it in class, that solution I'm glancing over because it's in the book, and here you have the final expression of the solution. You're gonna see a lot. So something that characterizes the class on heat transfer is that at some point you start getting lots and lots of formulas, and sometimes it's almost overwhelming, see so many formulas. But every time you get a formula, think of this, that getting a solution to these problems, the formulas we get are typically the result of 1 PhD per formula. And if I give you 10 formulas, that is about 10 people who spent 4 years trying to get them. It's amazing, right? And we're synthesizing all that in this class. So we did, we looked at the overall heat transfer coefficient in a pipe, and we made it to the point in which we found the solution and we started to discuss the solution. What did we see that was interesting? We saw that in this pipe in which we had a fluid going inside, water going inside, and we had air outside, we saw that we had the heat transfer in this case was a circuit with 4 resistors. 1 resistor was, 3 resistors. 1 resistor was the one of conduction in the pipe. And the pipe, because it's cylindrical, we use the formula for cylindrical geometries. And then there is the resistance of convection outside the pipe and the thermal resistance of convection inside the pipe. And when we add them all up, we saw that the thermal resistance of convection inside the pipe was small, the resistance of the pipe was super small, and the thermal resistance of convection outside the pipe was dominant, was the largest one, and was the one that controlled pretty much the whole transfer process. When we calculated the overall heat transfer coefficient using the outer surface of the pipe as the reference area, we got to the conclusion that the overall heat transfer coefficient was almost the same as the heat transfer coefficient of convection on the surface. And it's no coincidence, because on the surface, convection to still air was very slow. That meant the resistance was high and meant the resistance was dominant. So when we look at all the resistances together, no surprise, the overall heat transfer coefficient is more or less the same as the heat transfer coefficient that was by convection on the surface. That is one thing we saw and we discussed. We also discussed this point 2, in which we said that that we want, when we design a heat exchanger, the resistance, the thermal resistance of the elements of the pipes or plates separating the fluids, that should be very small, because we want the heat to transfer quickly inside the heat transfer, inside the heat exchanger. If heat transfers very slowly, that will end up being a huge heat exchanger, as we will learn to calculate soon. When we have a cylinder that has a thin wall, it gets to a point that if the wall is thin enough, you might as well assume that very thin wall is just like a plain wall, right? The same way we know that the earth is round, but you believe your table is flat. So we think it's flat just because it has a very small portion of change of angle, right? And if our table that looks flat was as big to the horizon, we would see that it curves. So the same would happen if the cylinder, if the pipe has a very thin wall. From the point of view of heat transfer, each point on the pipe would look like just as if it is flat. So what is the limit for this? How big should the pipe be so we can consider a plain wall? So if in a cylinder we consider that we use the formula for a thin wall, for a wall instead of a cylinder, the error is of the order of thickness divided diameter, right? And because we're talking about thin wall, it doesn't really matter if it is inner or outer wall. So in our case, we have a thickness that was, let's see, the thickness was 1 millimeter, and the diameter was 20 millimeters. So the error in this case, if we had done the calculation, assuming that the pipe is so thin that it behaves as a wall, there would be an error of 5%. If the pipe was even thinner, the error in assuming the cylinder is not a cylinder, but it's a plain wall, is even smaller. If the pipe is thicker, for example, the case of fiberglass insulation around a pipe, in which the pipe might be small, but the insulation is large, then this error starts to become bigger and bigger and bigger, to the point in which at some point nobody would want to accept that big error. For spheres, is the error in assuming that the surface of a sphere is just a wall instead of being an actual sphere. The error would be 2 thickness over d. So if we have a sphere of 1 millimeter wall and 20 millimeters in diameter, we can use the formula for spheres and calculate the heat transfer by conduction, and we would get a number. If instead we said the sphere is so thin that we can assume that each point of the sphere behaves just as a plain wall, then the error would be 2 times thickness, 2 millimeters divided diameter, 20 millimeters. That would be an error of 10%. So I'm going to ask you in the quiz to use the concrete cylinder or sphere formula if that's what I want. But if the wall is very thin, it's more or less the same. I will be clear in the exam. But the reason we might choose the formula with the error is because it's very easy to remember the formula for resistance of a wall. And it's more difficult to remember the formula for resistance of a cylinder. Sometimes if we're doing very quick calculations trying to design something, we might just want to cut some corners. Something else that is beyond 1D. So if in steady state conduction we're beyond 1D, this equation I have here is the general equation for transients in 3D with heat generation. The only thing I'm assuming here is that the thermal conductivity is constant. Otherwise, this Laplacian becomes more complex. If now we say we're in steady state, we can take this term out. If we also say there is no heat generation inside our in the material we're considering, we take this out, and the end result is this equation that is Laplacian equals 0. Now this is very interesting because this equation looks harmless. This equation looks so simple, and this equation is the equation for pretty much for absolutely everything that is steady state, no heat generation, and thermal conductivity more or less constant. Whether we're talking about walls or cylinders or spheres or Mickey Mouse, this equation is universal. Now, clearly the solution for a cylinder is not the same solution as a sphere, not the same solution as Mickey Mouse. And the difference, why the same equation can give different solutions, is in the boundary conditions. So in heat transfer, the key is in the boundary conditions. The equation, the differential equation itself became like very simple. But when we put the boundary conditions, might become very difficult to solve. So we can say some things about the final result before we do anything. And I want to introduce this concept of isotherms and adiabats before we get into more quantitative analysis. If you look at old exams, you're going to see that I asked every year for people to draw isotherms or adiabats, or to do comparisons or choose whether this is right or wrong. So I'll try to write. Last time I tried to do freehand writing, the computer crashed. So all those of you who have a religion, please start praying. Okay, let's see. Okay, let's share. Okay, you're seeing the whiteboard. So let's see. Isotherms are lines of constant temperature. And adiabats are lines of flow of heat. What properties each of these have? So isotherms define surfaces at constant temperature. For example, if I have a system, whatever its shape, but I pick one, let's say, our universal potato, and I were to say that this region, right? The boundary condition here in green is, this is a common boundary condition. That would be, this is an isotherm. This is then an isotherm. And there is another interesting property of isotherms. Isotherms never cross. That also means that isotherms are parallel to other you know what? Let's not say this because it's going to confuse. But let's better show it in action. So let's have a new whiteboard here. Let's say I have this surface here, something like this we have drawn many times. And let's say that this surface temperature is constant. The isotherms in this case would be all parallel to the surface. For example, if this was the case of a wall, we would have TS side A, TS B, and these isotherms would be parallel and until from going from one surface to the other surface. Let's do another one. Imagine we have a cylinder with radial heat transfer. Oh well. And we say we have, let's say this is TS inside, and we have here TS outside. The isotherms in this case, right, the heat transfer here is radial, and the isotherms would be, oh, it didn't make it pretty. Oh, that one did. Okay, so you get the point. I'm gonna make say these are isotherms. They never cross each other. They never cross each other, and they are parallel to the surfaces of constant temperature. The other thing we defined was the adiabats. So adiabats, they have this property. They are they're the lines of heat flow. They are parallel to insulated surfaces. They never cross. And of course, you can prove all this with math, okay? But if I give it to you as rules, we're good enough to start. And it's such few rules and so simple that we'll be okay. So they never cross. And the most important thing, they're always perpendicular to isotherms. And this is the interesting point. So let's see if I can, no. Okay, let's go back to our wall. We're back to our wall. And I'm going to make the lines of heat, the adiabats. The adiabats are always perpendicular to the isotherms. So the adiabats are going to be like this. These are the adiabats. They are always perpendicular to the isotherms. Always perpendicular to the isotherms. Oops. Oh, no, 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 no. Okay. I think the prayers were not strong enough. Let's see. So, okay, let's go little by little. We might be able to recover. Okay. Okay, so we're good. So these are the adiabats in the plane wall. So let's look at the adiabats in the cylinder example we looked at. Here we go. So the rainbow was kind of confusing. Let's choose. Okay, can I? Oh, I was hoping to give it a different color, but that's okay. So let's do the adiabats. The adiabats are always perpendicular to the isotherms, so they will be radial. They will be radial. And although I'm putting an arrow, that arrow would apply if so in this case, is if the inner temperature is higher than the outer temperature. So this is what I want you to know, especially that the isotherms and adiabats are perpendicular, and the isotherms or adiabats never cut with their own kind. Let's do one more. Let's consider this case. Let's say we have, well, this square here, and let's say that this side is insulated. Let's say that this other side is insulated. And let's say that this is T1 equal constant. And let's say that this is T2 bigger than T1 is also constant. So in this system, let's look at the isotherms. We know that the isotherms are going to be parallel to the other isotherms. Here we have isotherms. Oops, no, I didn't mean that. Okay. We saw that isotherms are what can I do here? Okay, let's see if I fix this. Yes, isotherms are parallel to the surfaces of constant temperature. But we also know that if a surface is insulated, this is an adiabat. So this is an adiabat. This other one is an adiabat because it's an insulated surface. And that means that the isotherms are going to be perpendicular. So here, they're going to be perpendicular. Here, perpendicular, perpendicular. Perpendicular in all cases. And we know the adiabats have this interesting property that they are perpendicular to the isotherms. So therefore, this is an isotherm too. And this is an isotherm. Same here. And sure enough, an adiabat is an isotherm, and here we had it perpendicular too. Oof. And because T2 on this side is bigger than in T1, the heat flux will go from high temperature to low temperature. Doing this type of analysis is even possible to make estimates of heat transfer by conduction in very complex geometries. If you take a look at the book, if you have the online version of the book, you're going to see it has a special supplement for this that is not in the paper version of the book. So you get to see isotherms and isotherms all the time when people show you these images of like colorful plots of numerical simulations. Okay, those are what these lines are. Isotherms perpendicular to insulated surfaces, and adiabats perpendicular to isotherms and perpendicular to surfaces of constant temperature. Okay, so let's go back now to our notes. Okay, so here we're back. Let's get the pointer. Okay, so let's talk about thermal resistance of something with an arbitrary shape. Let's say we got bored with cylinders and walls and spheres. Let's talk about weird stuff. And I'm going to show you an introduction to weird. It can get even deeper. But the beauty of this is that there is a way in which we can use very easily the solutions that took 4 years to a PhD, one formula at a time, to generate. We'll see two concepts that are very closely related. I don't even know why in the book they're listed separate, but I'm going to go along with that. The first concept is called the shape factor. And let's see what the shape factor is. So we know that the heat is the heat flux is proportional to the temperature jump between 2 points and the thermal resistance between those 2 points. There is a concept called shape factor that is defined as follows, such that the resistance can be separated as something that depends on the geometry and something that depends on the thermal conductivity. If you look, let's see what we had before. When you look at the thermal resistance in this case of let's look at the thermal resistance of a cylinder. You see here that you have some kind of math and then a 1 over K. This 1 over K, this K here, is the thermal conductivity. That is a material property. Everything else is a geometry, property of the geometry. So similarly, if we looked at a wall, right? The wall we have K, that is a thermal conductivity, and this L over A that depended only on the geometry. Similarly for the sphere, look at this. We have K here and something that depended only on the geometry that has units of 1 over length. So what people decided to do is say, okay, I'm going to define resistance in a very general way as something that is 1 over K that captures the material properties. And then all the rest, however difficult, however intricate, depends only on the geometry and has units of 1 over length. So I'm going to call this the shape factor. the 1 over the shape factor here, and shape factor will have units of length. But it's not any length in particular. It's the result of 4 years of PhD work by somebody that after they did the crazy integrals of the 3D partial differential equation, they came to this proportionality, and this is the constant of proportionality that they found with so much effort. So with this definition of the shape factor, if we replace this by resistance, we end up with the expression that the heat transfer, the rate of heat transfer is shape factor times thermal conductivity times the delta T. Delta T is our boundary condition. K is a material property. S looks so innocent, but S is a result of a PhD for each case. So before I get into the other thing, here we have examples. They are tabulated in the book of solutions for the shape factor. So let's say you have a sphere buried under the surface. Let me give you an example of where this applies. So the radiation is one of the forms of treatment for cancer. And for example, for prostate cancer, one of the ways of treatment is to put radioactive pellet, right, that have a heat generation under the skin, such that their radiation will kill like the bad cancer cells around. Now, they also get hot, and it shouldn't be so hot that it ends up causing more harm than good. So how would you calculate like the amount of the temperature of these radioactive pellets that are under the skin? You know how? You use this formula here. You use this formula here. This would be the radioactive pellet that is generating an amount of heat. And this amount of heat has to go through the flesh into the surface. So you might say, well, but aren't these formulas done for the case in which there is no heat generation? True. this formula accounts for the thermal resistance of the flesh. The flesh has no heat generation, at least in this simplified model we're talking about. So this is the flesh with no heat generation in steady state, and the pellet that has some amount of heat generation, but doesn't matter, it's just an amount of heat that is imposed. And that will result in a delta T that should not be excessive. Otherwise, instead of giving a patient radiation, you're just burning it. Isn't this amazing? And here you have the formula. This formula is something that neither you or I will be too quick to derive. This is small enough that is less than a PhD. But you need to know what you're doing, right? And the good news is we don't need to know. We just need to know where to find this formula. And for this geometry of a sphere under the surface of a large surface, semi-infinite, right? This is the shape factor. If we look at this equation here, it says that the heat generated by this pellet would cause a temperature difference given by the thermal conductivity of the flesh and the shape factor. And the shape factor is this. And something you're going to see a lot in this class when we get to discuss convection, lots of formulas that are plug and chug. So the formulas have a lot of ink, and you just need to find the different values and you put them in and you get a result. I will help you understand the vast majority of those formulas. Some of those formulas are merely empirical and just work. This class is often taught as just know how to plug and chug. We're going to do more than that. But plug and chug, we have to know how to do anyway. So look at this shape factor. D is the diameter of the sphere, right? This radioactive pellet, they tend to be millimeters in size. 2 pi, we know, D and Z. Z here is the depth of the center of the sphere under the surface. Let's look at another shape factor. Again, somebody else, this is simpler than a PhD, but not much simpler. It's a master's, let's say. Somebody looked, what if I have a long isothermal cylinder under a large surface? And you might think, this is so contrived. You know what this is? This is a pipeline running under the ground. I don't know if you know, but one way of knowing where the pipelines are is if you fly over in summer, the pipelines typically are buried. Not always, but in our province, most of the time are buried. And you know how you know they are there? Because in the summer, the grass is greener over pipeline. The grass is greener not because they get extra oil through the leaks. No, we have no leaks. But the grass is greener because it's warmer. And why is it warmer? Because the frictional heat of the oil going through the pipeline generates heat that makes the pipeline warmer. And that's the reason we see the grass greener. How do we know the relationship between the temperature of the fluid? Well, if we know the pressure losses, we can calculate the power losses, and that power is transformed in heat. So from pressure losses, we can calculate heat generation. And from heat generation, if we know the depth of the pipeline and we know the thermal conductivity of the soil, we can calculate, and we know the temperature at the surface, and then we can calculate the temperature of the fluid. This is super amazing. As a matter of fact, I have an example on this. And there are other examples. Let's talk about thermal conduction between two cylinders of length L in an infinite medium, right? And you know what this is? This is SAC-D. Of course, they didn't do it for SAC-D. They did it because, I don't know, they wanted to torture the PhD student and give them every time weirder and weirder geometries. But yeah, all these things have applications. This is the thermal conductivity, the heat transfer between two pipes. Of course, it's like this much more complicated because as because we have advection, we have transport of mass. But this is a good way to get started. So, and we have more and more shape factors for crazy things. Look at this. This is an edge. So let's say you want to calculate heat losses in a cooler, and the cooler is made of styrofoam and thick styrofoam. So you can assume the styrofoam is so thin that we don't need to worry about the edges. But let's say you want to do an extra good job. So let's say that the styrofoam is thick and each of these sides acts as a wall, and we know very well how to work with the wall. And the edges are going to have their own heat transfer coefficient. We know how to do it now because somebody did the calculation for this very complex problem of the edge. You want to talk about the corners? Yes, the corner of a fridge. Here we have. And many more, like let's talk about square pipes, right? And if you go to the literature, there's more and more and more because there's no end to the geometries in which you can give a PhD student to solve. And you and me benefit from this because after 4 years of work, all they did is got a formula like this. And every time we use a formula like this, for example, in an exam, we have to be so grateful that if it wasn't for this, whoever PhD student that did it over 4 years, it would be us taking 4 years to do it instead of 4 minutes to plug and chug. Okay, so that is the shape factor. In these 2 minutes we have, I'm going to introduce another way of tabulating the work of these PhD students. A weird geometry, complex geometry, we're going to tabulate it in a way that for us becomes just plug and chug. So, and it's called the dimensionless conduction rate. So we have seen how we can calculate a resistance using the concept of shape factor. Now, we can calculate the shape factor using this other dimensionless conduction rate. And it's defined such as that the shape factor would be a reference area, a surface area of whatever that would be. That can be surface of a sphere or surface of Mickey Mouse, a characteristic length. I'm going to talk more about this characteristic length. And this QSS star, that is a dimensionless conduction rate. Surface area is easy, characteristic length is easy. This QSS is where you have 4 years of a PhD put in. How do we calculate the characteristic length? We are going to typically use this value, and unless somebody explicitly says the opposite, this is what we are always going to use, and this is what anybody typically uses. Characteristic length is square root of area over 4 pi. Why? Well, if we're talking about a sphere, the characteristic length would be the radius of the sphere. So to some extent, this characteristic length is some way of turning everything else we know into some sort of a sphere, right? It's like a sphere equivalent. But from the practical point of view of implementation, it's just a formula where we plug in. It has a meaning. For a sphere, this becomes radius. Then how do we calculate heat transfer by conduction? Well, heat transfer by conduction Q would be surface area over characteristic length times this dimensionless conduction rate times K times delta T. The dimensionless conduction rate is typically used for shapes that are finite. For example, Mickey Mouse, and not for a pipe or not for an infinite wall. All right. I think this is a good point to stop, and we're gonna pick up here and go over 2 examples on Friday. Thank you very much, and I'll see you then.